Hey everyone, this is Dolis. I am a solution architect in Nirmata. Nirmata is the creator of Kyverno. Saurabh?
Oh, hello everyone. My name is Saurabh, and I'm an engineer at Outerbounds.
Perfect. So today we're going to talk about policy-based compute orchestration and how do you achieve, in today's AI world, how do you achieve your compute orchestration with the help of policies? But before we move and talk about the tendencies and the nature of AI workloads, let's talk about why we need policies. Like, we have been hearing Kyverno from since morning. We had one talk already, and we're talking about policies. We're talking about Kyverno. But let's take a step back, and let's understand why we need policies. Why are we all here talking about Kyverno, talking about policies? So this is a recent CNCF report, and there are some cutouts over here that I've pasted. All of these are like you would have hear about these in social media, some cluster going down, some security threat happening here and there. And the major reason because of this is misconfigurations. We all know Kubernetes is a little complex, a little dynamic. But that's not the problem. The problem really happens when you try to scale it up to a level where there are hundreds of developers working on it. And there are different teams that are touching your cluster. So it can be your security team, platform team, your developers, your operation team. And everybody kind of needs something else in the YAML. Security team is more about security best practices. Operation team is about scheduling. Platform is about developer experience. So everybody is kind of looking at different things in the YAML, touching the YAML at the same time. How do you make sure that not even a single misconfiguration is left, which can bring your entire cluster down, and it can become a vector for your hackers? When I say misconfiguration, it can be as simple as pod running as a root, or image coming from public repo, or not having the right labels and stuff like that. So it can be as simple as that. Now, this is all the ground covered. This is something that's a challenge today. Now think about, as we are going ahead with platform engineering, where platform engineers want to provide a self-service environment to their developers. Gone are the days where developer used to create a request for an environment, wait for like 2-3 good weeks, and then get an environment. With this amount of time where we want the CD cycles to be really fast and the application to hit the market faster, we want to provide self-service to the developers. How do you do that? Because you want to provide them a playground, but also you own the cluster. You are basically owning, you're the admin of the cluster, and you want to make sure there is no misconfiguration. But at the same time, you want to provide them a self-service environment. It's too good to be true. So that's when you require policies. What are policies? Now, we have policies in our real life as well. There are some known policies. There are some unknown policies. But we are living in a world full of policies. Policies are basically what you can do and what you cannot do, right? So we do have everything like these set of rules where we know what to do and what not to do. That's exactly what policies is. It's not very complicated. It's a set of rules that you tell your developers that, my friend, these are the things you can do. These are the things we should not do. Now, by that, what will happen is now you're enabling all the self-service for your developers, where you're providing them a playground, but it is a guarded playground. And you are owning the cluster, so you're also controlling any misconfigurations with the help of policies, but you're also giving that experience to the developers. And all these different complexities that I was talking about, all of that is something that you can manage when you have set of guardrails with the help of policies. As you may know, Kyverno is your policy engine. It was initially designed for Kubernetes, but now it's also, you can use it to do the same thing for your IAC, for Terraform, for Docker, for any JSON. Now, the reason that Kyverno is super cool is because you do not require any language to learn. If you're already familiar with Kubernetes, you know what how a YAML works. It's easy to write your policy. It's easy to get started. You have the full resource lifecycle management with Kyverno. It has integrated reports, because just having the policy will not cut it out. You have to understand, you have to visualize it, you have to see what is happening, how many of those are failing, passing, and then some workflows like exceptions and other workflows is something that Kyverno helps you to achieve. Now, that's just the context where we are going to go into the session. And what it is about is the compute we were talking about. And majorly, we're talking about AI/ML workloads, right? When we talk about AI/ML workloads, these workloads are often in batches. That means they can run for small duration of time or up to months. They can be training data. And the challenge over here is when you're running a batch where it is running on a training data, you really don't know how much resources it would require, right? You may say that let's deploy it on a cloud, you know? But cloud is neither free nor infinite. You cannot have a batch running in there, consuming all the resources required just because it is deployed on cloud. So there comes the complexity of managing your resources, managing your compute, making sure that the batch is running, have its resources that it requires, and it's not taking the resources for other workloads. Now, Saurabh is going to just put some light on this topic, and from there, we'll take it forward.
Awesome. Thank you, Dolis. So as Dolis mentioned, the crux of this talk revolves around how AI/ML workloads are different from, let's say, a microservice that you might be more familiar with that sort of runs on Kubernetes as a first-class object. A couple of things to sort of remember before we move on is AI/ML workloads can demand really, really large resources from your cluster, as well as the cost attribution of these resources in context of the value that they're producing is very, very heavily scrutinized at the moment. For example, if Meta, for example, is investing $600 billion in building out compute capacity, they definitely need to show at least $1 trillion of incremental revenue. Otherwise, why are we even doing this? However, before we move on more into the depths of Kyverno and how it helps us manage resources, let's sort of take a step back and figure out what is this entity that is even submitting these AI/ML workloads into a Kubernetes cluster. So let's take a step into the world of Metaflow. But what is Metaflow? Metaflow is a human-friendly Python library that allows you to develop, deploy, and operate AI/ML applications. Why is this important in the context of why we are here today? On the left-hand side, you see a triangle that is going from modeling all the way till data. That is basically trying to show you how much an AI or ML developer cares. So as a data scientist, you really care about modeling, which means that you want to be able to use any of the libraries, Python libraries that are out there in the wild in order to write some DAG, which will allow you to train data. Or you really want to be able to, once you've written up your code, you want to be able to deploy it in a production cluster with relative ease. You want to be able to version your data. So if on January 1st you wrote x equals to 5, and you ran your data on January 2nd, you do want to be able to go back, and you do want to be able to say what is the value that I assigned to x on the 1st of January, and if I change it on the 2nd of January to 10, what is the value that I had on the 2nd of January? Orchestration. Now, orchestration and compute are the two pillars that we are going to dive a little more deeper into as we move along. And finally, accessing of data. You want to be able to access your data from anywhere, whether it's in S3, whether it's in blob storage, whether it's in a database. You want to be able to get all of that. So sort of if we were to paint a homogeneous picture, let's say you are an AI or ML developer that has been given the task of use an LLM to extract information from loan applications to predict default risk. Now you're like, hey, OK, my data, in order to build something like this, the data that I need is sitting in a lakehouse, either in Snowflake or a Databricks. And the compute that I need is sitting either in a Kubernetes cluster or it is in an NVIDIA cluster that my company has. But I need this glue that will allow me to solve this particular business problem while taking in both compute from my clusters as well as data from my lakehouses. So consider the jobs that you need to do. You can have interactive workloads where you are, hey, I'm writing a code, I'm running it, and I want to see what the output of that particular code is. Or I want to have scheduled workloads where I have already written out the code, I'm happy with it, I've deployed it to a production cluster, and it is running, let's say, at 7 a.m. every morning, Pacific time. Or I could have distributed training workloads, post-training workloads, inference workloads, and something that all of us are trying to get out of the door these days, agentic applications. Now, let's sort of dive in as to how Metaflow allows you to do all of this. On the left-hand side on this picture, you see a Metaflow flow. A Metaflow flow is nothing but a composable function which are annotated with this decorator called @step, and essentially it allows you to write DAGs, directed acyclic graphs. Once you've sort of written this DAG and you're happy with it, then you can run it locally. You can run it on your Kubernetes cluster, or you could deploy it for scheduled execution via something like an Argo workflows. So in this particular diagram, as you can see, the stick figure, in this case, my data scientist, goes and says python flow.py run -- with Kubernetes. So once you've written it, you don't really need to build any machinery to move that code from your local machine over to the cloud. And Metaflow will basically ingest this particular DAG, and it will create CRs, whether they are jobs, job sets, cron jobs, and the Kubernetes machinery will take over from that point forward. Now, this Kubernetes machinery can live in GKE, AWS, Azure, or any of the neo clouds that you might have heard of, CoreWeave or Nebius. Now, something more interesting that Metaflow allows you to do is, as you can imagine, let's say, take the example of a data set that is spanning over the past 5 years. It is going to be very, very time consuming if you were to take a single computer and you were to run this entire data set through that single computer for your training workload or for extracting insights from that data. So what Metaflow allows you to do is it allows you to fan out your workload across many, many computers using a very, very straightforward semantic called for each. As you can see in the diagram over there, all you need to do is you need to create a list of things that you need to input into every particular workload, and then each of the functions, in this case the train step, will become a separate pod, which will take the input from the parameter that is in the start function. And then the execution sort of looks like the following. So with all of that history and with all of that background as to why, as to what and how these workloads end up in the cluster to begin with, let's sort of talk about and reinforce some of the policies or policies as code which define the guardrails for such an execution, and why do we deserve these guardrails? So workloads, for example, if you can think about it, workloads that execute only on CPUs should not run on GPU nodes. Like that will, unless and until you really have a lot of money to throw around. No single workload should be able to reserve all the resources in the cluster. So there should not be a situation where one workload comes in and says, OK, I'm going to take up all of these nodes that are available in my cluster. You should be in a situation where you're able to route workloads to compute pools or node groups to achieve either minimization of cost or maximization of resource utilization. You should be able to minimize resource contention. So it should ideally not be the case that there are multiple workloads that are waiting to get scheduled onto a node group, and there's only so much limited compute that is available. And you should prevent noisy neighbors from interrupting workloads. So you can consider the fact that you have a single workload that is running on well, you have, let's say, 3 different workloads that are running on a compute node, and 2 of these workloads don't have any limits that have been assigned to them, and suddenly they are taking up all the resources that are available on the node, and leading to evictions of pods and failures of other pods, which are nothing but other AI/ML workloads that are also scheduled on that particular node. Workloads should only be able to use images that have been blessed by infra teams. I mean, it'll be pretty sad if a bad actor was able to schedule workloads for Bitcoin mining on your super expensive GPU nodes that are part of your cluster. And assigned infra should be beefy enough to satisfy effective resource requirements for a pod. This one is sort of important because there is always this trade-off where you have to choose either between a quick startup time for your workload or the lowest cost that you want to spend on a particular workload. And last but not the least, data scientists must remain unaware of infra semantics. As a data scientist, the one thing that we often hear from them is, how much compute do I need to run my workload, or why do I even care that there's a GPU compute pool with only 5 nodes in it, or there is a CPU compute pool with only 2 nodes in it. I just need compute, please run my workload. So the problem of the day, how do you match incoming AI/ML workloads to compute? The compute requirements vary by workload, and so does the compute shape or availability. CPU and GPU node groups can wildly vary in terms of the hourly costs across on-demand instances or spot instances. Workload priority also dictates the desired properties around quickest startup time or lowest cost. So as you can see, there are 3 workloads. The first one is requesting 2 vCPUs and 8 gigs of memory. And the second one requires a GPU, and the third one requires really, really large amount of ephemeral storage. So what is this? How do we plug the question mark in the middle to make sure that all the guardrails that we've already talked about are enforced when moving these pods to node groups? So Kyverno to the rescue. Kyverno has this concept of external variables, which support Kyverno to learn about available compute options. So you can consider a situation where you have this upstream controller that is reading the state of the world as it exists and puts that information into some data stream or some data point, which is, let's say, a config map in this example. You then utilize preconditions to enforce your business rules. For example, workload priority has to be considered when you are mapping a particular pod onto a spot instance versus an on-demand node group, or you have to, and then you can sort of mutate node affinities or node selectors to route a pod to the correct node group. In this case, or in this example that I have seen, that I've selected, you can see that in my config map, I have node group A, B, C, and D, and each of those node groups is basically saying that on node group A, I have 16 vCPUs and 64 gigs of memory. On node group C, for example, I have 8 CPUs and 32 gigs of memory. And on node group D, I have 8 GPUs as well. So now assume that the third pod, the pod at the bottom, was asking for GPUs. Then you can have your rules in your policies in Kyverno Kyverno, which has sort of already ingested the config map as an external data source, knows that, hey, there is this particular node group that is advertising GPUs. So my pod is, which is asking for GPUs, I can go and at least place this particular pod on that particular node group. And I should not place it on A, B, or C, which do not even advertise GPUs. Let's take another example about running blessed images. Now, if we were to extend the example that we just saw about external data, assume that in your config map you had put in a bunch of images that had been blessed by your infra teams. In this example, I have blessed image 1 with a tag of dev A, stage B, but I have left out a specific tag for prod, and I'm happy to allow any images that are prefixed with the prod tag. Now, what does your validate policy look like? You basically write a deny policy, and you say, hey, I'm going to deny anything and everything that in a pod spec with an image that does not exist in this particular list that I've given. So for example, let's say a pod spec comes in, which is asking for an Nginx latest. This pod is not going to get allowed in because the image on the example container was not something that was present in your config map. Whereas if there was another pod spec that came in and it asked for prod latest, then it is going to be allowed. To get through. A couple of important points here. The validate policy use the any not in operator, which allows you to have wildcards, and as well as another good thing to remember is, given the fact that you always have an external controller that is always updating your external data source, you could always build a pipeline that can update or add or remove things from your external data source at any point in time. So for example, let's say you said, oh, you know what, I just discovered a 0-day vulnerability in my dev A image, so I'm going to yank it out. You can just go ahead, yank it out, and the controller will just go ahead, reconcile the information in the config map, as well as your Kyverno policy is going to start enforcing it, which is why this is such a powerful paradigm. Now let's take a look at another example. CPU workloads should not route to GPU node groups. I mean, we've seen people try to do that for various good reasons, but as a matter of policy, let's try not to do it. So let's take the example of a mutation policy, where in the precondition, you can say that, hey, if any container is asking for NVIDIA GPU resources, and it has to be greater than equals to 0, then I'm going to put in, let's say, a node affinity with a key and value of GPU node group. And essentially, I want to route it to a GPU node group if and only if it requests a GPU. So let's take the example if you have a CPU-only workload that comes in, where essentially what that means is in your request resources, there won't be any NVIDIA GPU limits. So you'll ask for 250 millicore CPU, 128 MI of memory, and 1 GI of ephemeral storage. This will not go to your GPU. Why? Because the precondition will fail. Or the precondition will skip, and it'll say, no, because I have greater than, actually this should have been greater than, but because it should be greater than, that's why it is not going to go to a GPU. Now, now let's say a GPU workload arrives. There's going to be an NVIDIA.com GPU 1, and Kyverno, the precondition is going to pass, and your GPU workload gets mutated with an affinity, node affinity, which says, your selected node group should be a GPU node group. So we've established that Metaflow has a lot of powerful features that allow you to scale your AI ML workloads effortlessly to the cloud. But simply scaling to the cloud is minimally required, but not sufficient. And Kyverno sort of steps up and provides easy constructs to ensure that your business policies can then be enforced as a last mile of defense, as well as it allows you to write validation mutation policies very, very easily. Namespace cluster policies provide flexibility across a wide variety of use cases for each, and external data sources are a very powerful combination. And patches JSON 6902 support allows for precise surgery to manifest at runtime. So how does this worldview look now that we have both Metaflow as well as Kyverno in the picture? As I said, Metaflow is the construct that will allow you to very easily move your workloads from your local machine over to the Kubernetes cluster. And once it is there, enforcing your business rules is the job of Kyverno that can make sure that every single pod that you're running in your cluster is adhering to the rules that your compute admins, your business leaders, your leadership, that they define. However, there are certain challenges that still remain even after we do implement all of this. First, this does not replace the need for an autoscaler or a scheduling layer. while Kyverno can be, we have leveraged Kyverno to target AI/ML workloads to respective node groups, it is by no means a replacement for the scheduling layer. Effective node group targeting is only half the battle won. Workload optimization challenges are not eliminated completely. Node groups could fail to scale. I mean, we've all been there where AWS might not have enough capacity available in a particular region, or for some other reason, the node group fails to scale, and the cloud vendor capacity is completely maxed out. Preempting workloads to allow more important workloads to execute can still lead to wasted human effort and infra cost. On the surface of it, it makes a lot of sense. Hey, if there's a low priority workload that is executing, I want to preempt that and bring in a higher priority workload. But what if it had been executing for 7 hours? It will lead to wasted infra cost, and not to mention the human effort that it took in order to write that workload, to develop that workload, and put it to production eventually. There is always a trade-off between bin packing and unused capacity. You can always consider that, okay, I have this node which has great resources, and I want to bin pack it to the maximum capacity. But if you do that, do you end up with noisy neighbors? If you want to prevent noisy neighbors, you leave a little bit of headroom, but then aren't you wasting unused capacity? So there's always that trade-off. And the compute landscape is ever-changing. There are always newer GPU architectures that are being released. There's a lack of compute in specific AZs or regions, which makes teams evaluate their data strategy. So if there is a particular compute instance that is only available, let's say, in US East, it might not make sense to have your data set present in US West. And because of that, it's causing a lot of teams to move to a hybrid cloud strategy where they are like, okay, I do want to guard against the fact that US East might go down at any point in time. So if that happens, I will move all my AI/ML workloads over to a different cloud. So that was my talk. Happy to take questions. Yes, please. You can. Do you want to give me a mic? Oh, sure.
So wouldn't there be some kind of conflict if you're running Carpenter to define your node pool and the kernel is setting the policies for the resource that can be used on that node pool? How do they work together?
Great question. So the question is, won't there be a conflict if you are running Carpenter, which is always trying to bin pack workloads, and then you have Kyverno that is trying to push workloads onto a different node group? Is that right? So the answer is it depends. We have seen situations where customers do ask for Carpenter to be running in their actual production cluster. Whereas most of the times they're like, let's not mess with Carpenter. We'll just manually control what kind of node groups are available, are hooked up to our autoscaler. So most of the times, dev clusters are where you require, like, they opt for Carpenters because they're like, I don't really want to spend a whole bunch of money on my dev clusters, but my production clusters, I don't care. Like, I do want to have guardrails as to how much any workload can spend on that particular cluster, but most of the times they generally avoid having Carpenter as far as AI/ML workloads are considered. Again, it is a good option to have for workloads like microservices. To have Carpenter deployed, but as I mentioned, for AI/ML workloads, the property that it can be very, very short-lived, whereas the runtime can, or it can be very, very long-lived, is important to be considered, because as I said, the more amount of time you spend executing your workload, the harder it becomes to decide whether you should preempt that workload or cancel that workload, because you then have to go back, especially on a GPU, because if you do preempt it, and you have to restart from the beginning, that's all wasted infra cost and human cost. So then you need other solutions like, okay, how do I checkpoint and how do I save my state so that I can start exactly from where my workload was preempted? And that is also the consideration to be made, whether you want a spot instance or an on-demand instance and so on.
Just to add to that, in Carpenter, you can define whether you want Carpenter to spin up spot instances or GPU instances. You can configure what you want Carpenter to spin up. Now you can have a Kyverno policy because you might require, like there might be a pod running, you can have a mutate policy telling your pod that get deployed on the node which Carpenter spins up. So it is, I would say rather it's not a conflict, it runs together because for Carpenter as well, you can then control using a policy what nodes you want to deploy, what pods you want to be scheduled on the nodes if they are deployed by Carpenter by using that label. So you can tell the pod that if this is the label and this is a GPU node coming from the Carpenter, because every time the node gets pinned up, there's a label that Carpenter also adds, right? So you can then have a better control because now you can tell your workloads that, listen, you get deployed on the nodes Carpenter spins up, and this is the validation logic where you look for the label, look for the node, and get deployed there. So now you'll have better control of that.
Then, now you have pod affinity, you have Carpenter, adding layers, and then you have Kyverno. So
It becomes, yes, it becomes a little complicated, I would say. If you're using Carpenter, then adding just that mutate label to your pod so that it gets scheduled on the node would be good. But if you're having like different pod affinity, different rules, then you have to sit and draw that logic and see how it fits into the picture. But with the policies, what it helps you is it helps you to give that control, whether you can decide where it wants to get deployed. If you think that Carpenter is spinning up the nodes and pods are getting scheduled, then you don't need a policy there.
is there a way to use Kyverno to ensure that pod are scheduled across AZs for HA purposes?
Yeah, so
Can I take that?
Yeah.
So, the scheduling of a pod across AZs can, I would argue that that is not a Kyverno concern. It is a concern of how you set up your node groups and what are the properties that your cloud provider associates with the node group that has been set up and how it auto-scales. It's more of an auto-scaling behavior rather than a Kyverno behavior. OK, I think we are at time. So we are going to be around. If you have more questions, happy to always take them offline. Thank you so much.